Welcome. This is Lynn Baker, a coordinator in the Office of Early Learning with the West Virginia Department of Education. This is the first of a series of 4 sessions that will focus on the standard algorithms in the West Virginia Next Generation CSOs. Today's session will focus in particularly with addition. My email address is on the front slide here. Please feel free to contact me if I can be of further assistance for you or to provide additional clarification. The standard algorithm within the next generation CSOs first begins in 4th grade, is where it's first mentioned. Prior to this time, it has been teachers are building background information that teachers in 4th grade will then use to transition students to becoming fluent with a standard algorithm. In 4th grade, the focus is on addition and subtraction. Multiplication is with 5th grade. Division is not until 6th grade. So the session 4 will focus on those foundational skills that we'll be using in 4th and 5th grade to help students develop an understanding of division so that when they're in 6th grade, they will be able to transition into using the standard algorithm for division. This session has used the following resources as it's been developed. The Standard Algorithms in the Common Core State Standards is a paper written by Karen Fuson and Sybilla Beckmann. You may find it interesting. This will be used in all 4 sessions as it addresses all 4 operations. The progression documents, in particularly number and operations in base 10, which was written by the Common Core writing team, also gives us some further insight. 2 print resources were used. Elementary and Middle School Mathematics Teaching Developmentally, the 8th edition, as well as Teaching Student-Centered Mathematics, grades 3 through 5. These resources were used as they were developed. They're print resources. Several of them have been used in additional professional development, so you may be able to put your hands on those easily. So let's get started. Our question is, what did the writers of the Common Core Standards for Mathematics intend when the standard algorithm was included in these standards? The Journal for Mathematics Leadership, an article by Reyes and Thomas, noted the following. There is an expectation for students to use the standard algorithm. However, a definition for the standard algorithm is not offered. If the authors of the Common Core Standards for Mathematics had a particular standard algorithm in mind, it was not made explicit within the standards. I find it interesting that the term standard algorithm, not traditional algorithm, is used in the Common Core Standards for Mathematics. Terms within the standards were carefully chosen to convey meaning. Something to ponder is the slight difference in the 2 terms. In my personal opinion, traditional seems to imply the way we've always done it, whereas standard implies a common method. In other words, a common method of conveying understanding. So what is an algorithm? Bill McCollum, in the progression document on numbers and operation in base 10, defines it this way. In mathematics, an algorithm is defined by its steps and not by the way those steps are recorded in writing. With this in mind, minor variations in methods of recording the standard algorithm are acceptable. In other words, students, it's the final product. It's that written record that we're looking at, not necessarily which stroke a student wrote first or second. Within the standards, we have the term strategy and algorithm that's been used to convey different meanings. A strategy focuses on students making sense of a particular problem. The strategy may work for that problem, but it's not always generalizable to a larger problem or to a problem using larger numbers or into a different problem altogether. This strategy was designed so students could make sense of a specific problem, whereas an algorithm is a systematic written method for recording steps. Sometimes longer methods become abbreviated as students gain proficiency with different procedures. They rely on the decomposing of numbers into base 10 units, and they're usually generalizable to large whole numbers and to decimals. Here it really comes to the understanding that students need a very strong understanding of our base 10 number system, which is developed in grades prior to 4th grade. So here's the 4th grade standard that talks about using the standard algorithm. Fluently add and subtract multi-digit whole numbers using the standard algorithm. Algorithms become helpful when we're using larger numbers, not just simple computation. This prior to the 4th grade, students have worked with numerous strategies that focus on making sense and developing a strong understanding of addition and subtraction, as well as our number system. Some materials use the term invented strategies. I prefer the term Jonna Bollier, the professor at WVU, used, and she termed it as student-created strategies. Even though the standard algorithm is the focus of 4th grade, it most likely will occur in previous grades. It's impossible to keep it from occurring. Parents will show their students how they solved these problems when they were kids. As educators, we need to be careful not to pass judgment on the varied strategies, preferring one over the other at any given grade level. And these simply become part of our toolbox that we use as we solve problems. When we begin working with the addition algorithm, students need a strong conceptual foundation of what is addition. It builds on the understanding of a base 10 system. And where are these developed? These are developed within our K-3 curriculum. Algorithms, they have advantages. It really makes it easier when we work with large numbers. But it also requires explicit instruction, and this instruction needs to focus on developing understanding, not just on procedures. Too many times, students learn these meaningless procedures. They develop error patterns that require an excessive amount of reteaching and remediation. Students need time to work with strategies they've created. If they have a deeper understanding, it will be much easier for them to transition into the standard algorithm. So how do we do that? We begin with models. Students have worked with models from the early grades and continuing into 3rd grade. Students need multiple opportunities to work with models. Then they will develop a written record alongside a model, and then eventually they will have the written record without the use of models. In order for a student to be fluent with an algorithm, they need to be able to complete it without the use of visuals. Now, when that occurs is sometime during that 4th grade year is the goal for our standards. The standard algorithm has different variations, but there are some things that are similar among all of them. They always involve different kinds of steps, so there's different steps they take in order to complete it. We need to keep in mind the initial number might be unchanged, or a single-digit numbers can be written so as to change the original numbers, and both have been accepted. Some students may prefer to calculate from left to right, the way we read. That does not take away that does not make an algorithm non-standard. It becomes that standard because it makes sense. It's not the order the steps are created in, but it's the written record that students create in order to convey their understanding. So let's take an example. Here's the use of a model. 37 plus 14 using base 10 blocks and a 10 frame. So we have 37 plus 14. A student has modeled that with base 10 blocks and a 10 frame, a form that they're fairly comfortable with. They've moved some of those ones in order to compose a new 10. So now they have a 10 frame. They realize the 10 frame is full and they can exchange that for a 10 block. So when they've exchanged that, they notice now they have 5 10s and there's one still having 1 1, so the answer is 51. Students need multiple opportunities to have this type of tasks that they can work with. So they're using models over and over in order to develop the understanding. We're not worried about how do they record it. We're worried about are they able to model it with the manipulatives that are there in order to develop understanding. So as we move forward a little bit, we also have a written record beside of a model. So this is kind of combining both of them. So we have 37 plus 14. We have 3 10s, 7 1s, 1 10, and 4 1s. So a student then begins to work. They've combined their ones, they've regrouped them, and they've composed another 10. And they've recorded that action on their record. Notice here, they've written down the 1 in one's place, and they've regrouped and made a 10, and they've written it up here. This is a way they're modeling their thinking in order to solve this problem. We need to realize as they understand it, as they work with this algorithm, they also need to share the understanding. This is not just simply adding a 1, but it is adding a 1, 10, and they need to have that understanding that they're able to share. Eventually, they add 1 10 plus 3 10s and 1 10, and they have 5 10s. And so my answer is 51. So now they've actually completed the algorithm. They've modeled it. They have a written record of what they have done with their with the models that they were using. So students, this works with small numbers, but as we move to larger numbers, it becomes more cumbersome. So let's look at the way it would look as if they were only simply giving us the written record. So here's 4 possible algorithms. Each of them would have been considered acceptable within our standards, within our next generation standards, and the intent of the authors of our Common Core. The first one they've added by places, so they've had 400 plus 100 gives you 500, etc. They've had some intermediary steps here, so this might be a transitional type algorithm as they're moving into that standard algorithm. It is a written record. They're able to do it without models, but it has some extra steps there, some extra things they have to keep in mind. The places have to be lined up, or they may lead them to having an incorrect answer. Look at the second problem there. They chose to show their regrouping underneath, below the first 2 numbers. It's still in the right places. It still gives us a right answer, 623, and that would be an acceptable under the term standard algorithm. Notice the third one. It kind of looks a little bit like subtraction, where they've actually marked a number out and then they've added the 10, where they've regrouped a 10. So it kind of looks like they've changed the number a little bit as they've moved forward. As we look at this, we need to be careful and make sure students understand what they're doing. But if they have an understanding of it, and this is the method they choose, this could be considered an algorithm that would be standard. And finally, one that might be more familiar to us, where we've regrouped and we've carried, might be the term that we've used commonly, but we're really looking at we've composed another 10, and this record here where we've written the 1 above the 10's place is giving us that written record that we've taken the 1s and we've composed it into 1 10 and 3 additional 1s. And so what the standard algorithm gives us is a written record of our work. And we want students to be comfortable with explaining that as well as completing it. It might be better for us in our classroom instruction to have 1 or 2 good problems with lots of discussion as we make this transition versus practicing a lot of problems without meaning. And so just because I can complete the procedure doesn't mean that I have a strong understanding. So distributed practice over time, a couple problems from time to over multiple days will give us that opportunity in order to solidify that understanding, because it's not enough to complete the algorithm. They need to have understanding of it. So in conclusion, when we develop fluency to that standard algorithm, our students need a strong understanding of base 10, our base 10 system, which is developed early on, which is that importance of those primary teachers and into 3rd grade having a strong foundation, developing a strong foundation of our number system. Beginning with models. This does not mean the 4th grade teacher began with models, but those models are beginning early on. We're developing a written record. That written record is a way for us to convey meaning, and we develop fluency by using the standard algorithm. And they determine within the progression document and the works that I've read, fluency with the standard algorithm means they're able to complete it without the use of visual models. Now, we sometimes jump too quickly to the use of that standard algorithm. We need to make sure students have plenty of time to work with models, so as they make that transition, they're able to make it with understanding. And above all, we have to make sure students are able to explain why that algorithm works. Why are they able to get the correct answer? I want to thank you for participating in today's session. Our next session will be on standard algorithms and subtraction, and we hope to have it available in December of 2013 to share. You will find this and other additional resources on the Office of Early Learning website at the address listed on this slide. So thank you. for participating today, and we look forward to working in the future. Once again, this was Lynn Baker with the West Virginia Department of Education. Thank you.